Okay, guys, so today we will be learning about the angular momentum in case of a rigid body. We are studying a rigid body and especially when it is rotating around a plane of axis, or we can say a rotation axis. So this is the axis of rotation and this is the rigid body. And the whole mass of the rigid body is considered to be m, and the angular velocity with which our rigid body is rotating is omega along the z-axis. So I will explain to you why it will be along the z-axis. Okay, as we know, rigid body is made up of large number of elements. In this case, let's say one of those elements is m, have the mass mi, and from the axis of rotation it is at the ri displacement. So Ri, it's the displacement position vector, we can say, and Mi is the mass of that element. No, no. So and it has the linear momentum Pi. It is rotating around the axis of rotation and with the linear momentum Pi. So angular momentum will be how much? Angular momentum Li vector, or let's keep it small l. Li vector will be, as you know, it will be the cross product of r, that is the position vector ri with the cross product the linear momentum pi. And now this is the cross product. So here when we can write this cross product as ri magnitude pi magnitude sine 90 degree. They have the angle of 90 degree between them. So in this case sine 90 is the angle, and the direction will be in the z-axis, because the plane at which the rigid bodies or the element is lying is the xy plane, and we know that angular momentum is an axial vector. Axial vector means in order to find its direction you apply the right hand thumb rule. So ri and pi, they are in the xy plane, so their direction of the resultant, that is the li vector, angular momentum vector, so it will be in the upward direction with the right hand thumb rule. And also we know that sine 90 is 1, so li vector will be ri pi k cap. No, or we can also say that it is, what is pi, what is angular momentum? Mass into velocity. So ri mi vi k cap. No, also we know that our omega is, or we can say velocity is r omega, angular velocity and the linear velocity. So vi is equal to ri, or and omega is product. Let's keep it omega for now. Okay, so li vector will now become mi ri square and omega k cap. Up to now this is the angular momentum. Let's take this as the equation 1. Now this is the angular momentum of the element mi. Now what if we have to find the angular momentum of the whole rigid body? So simply the total angular momentum of the rigid body, then what will we need to do? So total angular momentum can be found of a rigid body. So we can find it by summing up all the individual angular momenta of all the elements. So we can write it as summation mi ri omega, and outside it will be the k cap, because all the elements in the xy plane of the rigid body, their direction will be upward according to the right hand thumb rule. That's why the k cap. So we can say omega and k cap, they we can take them back because they don't depend on it. Omega is same for the rigid body for all of them, omega k cap, and inside it will be summation mi ri square. It is the square actually. So now, but we also know that what is miri or mr. So summation mi ri square will be moment of inertia. This is the definition or the formula of the moment of inertia. So about an axis of rotation, about this axis of rotation, the moment of inertia of the body, the moment of inertia of the rigid body will be this. So now we can write L as L vector will be, let me write it here. This implies L vector will be now omega k cap I. We can write it as I omega k cap. Or now we can write the omega or angular velocity as the vector omega, and k cap is showing the direction in which the vector is uh, going. So L will be equal to I omega vector. This is the angular momentum of the rigid body about a fixed axis. So direction of L and omega. So direction of L and the omega, both L and the omega, their direction will be in the z axis, because there is a k cap with this, so it will be along the axis of rotation. Their direction will be along the axis of rotation. Now let's understand the conservation of linear momentum. What does that really mean in case of the rigid body? Conservation of angular momentum. Angular momentum. If someone asks you to derive it and how to write it in mathematical form, then you can use this. So we already know that L is equal to I omega. We know that we have derived it. L is equal to I omega. Now differentiate both sides. Differentiate both sides with respect to time, respect to t. What we will get? Now we will get now we'll get dl by dt equals to d by dt I omega. So I omega, we have just differentiated it. And one more thing about the angular momentum that we have derived earlier in earlier sessions. Let L is actually time rate change of the angular momentum is actually equal to the torque, just like the, we can say it as the uh, angular analogous of a circular analogous of the second law of motion, Newton's second law of motion, that a deep force, external force, is equal to the rate of time rate change of the linear momentum. In the same case, in the same way, dl by dt will be equal to tau net, net external or internal, both, a net torque. And let's put the value of L here in this equation. So it will become d by dt I omega is equal to tau net. Now what happens if the external torque acting on the body is zero? Okay, if the let's say only the external force working, or the external rotational force, that is the torque working on the body, is zero, then d by dt I omega will be equal to 0. What does that mean? So when is the derivation of something is 0? See, when is the derivation of something is zero. It's only possible when this thing itself is constant. It does not change with time. So I omega is going to remain constant. Only then d by its derivation can become zero. What does that mean is, let me erase it. So this means that I omega is constant. Now if it is constant, or we can say L is constant, that the angular momentum remains the same. This is the law of conservation of angular momentum. This is the law of conservation of angular momentum. Now, let's say the moment of inertia of a body, like of a body, changes from I1 to I2. I1, it was before of rigid body. It was I1. Let's say its moment of inertia was I1. Then it became I2. Why it became I2? Let's say it became I2 as a result of a change in the internal distribution of the particles. Okay, no external torque is being applied on the body still. It's an isolated system. No external torque is applied. So let's say if you change its own configuration, it's the body changes its own configuration because of internal forces. Okay, the mass, its distribution changes, or its shape changes in itself. So that's why I1 will now become I2. And the angular velocity changes from, it was omega 1 at first, and then it changes to omega 2 due to internal change in internal distribution of mass, due to change in internal distribution of mass. We got two moment of inertia and respective angular velocities. So, but remember, the law of conservation says what? It says that if external torque is not being applied, if there is no external force whatever on the rigid body, then its angular momentum should remain the same. It should not change. So it if it was I1 omega 1 before, so it should be equal to the I2 omega 2 even after there is a change in the internal distribution of mass. Condition is that external torque should not be there. The tau net should be 0. There should not be any change in the net torque. So I1 omega 1, let me write the vectors as well. I1 omega 1 is equal to I2 omega 2. It's just like the third law of Newton's motion. So it will mass into acceleration. Yeah, force. Every action has its equal and opposite reaction, but it's a little different in the circular motion. So I1 omega 1 will be equal to I2 omega 2. Now let's and one more thing I would like to add before practicing a question based on this conservation of angular momentum. I would like to tell you that omega is actually equal to, how do we relate it with the, let's say, time? So it will be equal to 2 pi by t. This is the relation, and we know that frequency is equal to 1 over time per second. Frequency is per second, so we can also write it as 2 pi mu. Mu is for the frequency, not the velocity. So omega is 2 pi mu. This is one of the relations that you will use so many times. So let's try a question based on this. There you go. So the question is, let's say of the earth, which has the, let's say, uh, the size that it has presently. So what happens if we contract the size of the earth equal to half of its size? We somehow earth contracts. Let's say its gravity increases a lot, and then it will contract in itself, just like a black hole. So what happens if the earth were to suddenly contract to half of its present size? If it is, let's say, its radius is r, so half of its present size, the new radius of the Earth will become r by 2. So they're asking, how will it change the day timing? How will it, how much it will change the timing of the day? On what will be the duration of the day in that case, where the Earth is half the size? Remember, the mass is same. Mass is same. So, and we also know that Earth is a sphere, and for the sphere, we have moment of inertia equal to 2 by 5 mr square. And a sphere, it's a sphere which is filled. It's not a hollow sphere, but a simple sphere. So for that, 2/5 of the mr square. So this is already given. So before contraction, let's say before contraction, I1. Let's keep it I1 for the present moment of inertia. It will be 2 by 5 mr squared. This is already given. Now after contraction. After contraction. Now after the contraction, the moment of inertia of Earth I2, it will be 2 by 5 m. It will still be a solid sphere, so it will be 2 by 5 m. Mass is same, but radius has now decreased to half of its size, so r by 2 square, which is 2 by 5 m r square by 4. This is the new moment of inertia. Now, how can we apply the conservation of angular momentum? In this question, there is nothing given that there is an external force working out there. So you can definitely apply the conservation of angular momentum. That means whatever the angular momentum was there before, it's going to be same. That means according to um, conservation of angular momentum, we know that I1 omega 1 should be equal to I2 omega 2. Now, as I told you previously, that omega is actually equal to 2 pi by t. See, how we're going to convert this angular velocity to 2 pi by t? Because we have to figure out what will be the change in the timing of the day. It is 24 hours at the present size of the Earth. We will find out what will be the how many hours will there be in one day if the size decreases to the half of its present size. So I'm going to write it as let's write it I1 2 pi by t1, and it will be equal to I2 2 pi by t2. You can pause this video and try to solve this now. We know the values of now we can write it as t2 is equal to time to we cross multiply, and 2 pi cross off, it will be equal to I2 divided by I1 into T1. Now you can substitute the values of I1 and I2 from equation 1 and 2, and we can see that T2 will be equal to 2 by 5 mr square by 4 and 2 by 5 mr square. They will cross off, 2 by 5 will cross off, and there was a t1 here as well, so t1 is here. So in other words, 4 will be down here, so this implies to t2 will be equal to t1 by 4. And the new timing, the new number of hours in the day will be a quarter of the, or 1/4 of the number of hours we have right now. So what is t1 originally? At present, time for one day is how many hours? 24 hours. That means T2 will be 1/4 of that. So it will be 6 hours. So see, it's very interesting. Like if you decrease the size of the Earth, half of it, what it is presently. So the day will become only of 6 hours. See how this impacts, and we have proven it right now and observed it by using the law of conservation of angular momentum. Right. So this was the one of the examples that I give, and after that, let's understand how the conservation of angular momentum is used by us in the real life, and we can understand very various natural phenomena uh, which can be explained using the the conservation of angular momentum. First example is a very simple one. It's a very interesting one as well. You can try it if you have a rotating chair. So let's say a man is sitting on a rotating table. It's a chair in this case in the picture. So, and his arms are stretched. His arms are stretched right now. So no, and he's rotating. He's rotating with the angular velocity, momentum of I omega. Angular velocity is omega, and I is the moment of inertia. In rotation, we don't take mass, so but we take moment of inertia. So it is I omega. See, here the I is bigger. Why it is bigger? In the case of where the man's arms are stretching outward, that is from the center of axis of rotation, his distance is bigger. See, we know that I is equal to mr square. So if r is bigger, I is obviously going to be bigger. That's why I is written in a big size here, and omega is small. That means you will feel like the person is rotating with the angular velocity which is smaller. Let's say when he withdraws his arms around his chest, there is no external force applied right now. He is just from stretching, he has just withdrawn his arms closer to himself, closer to the center of axis of rotation, sorry. So this in turn, what it will do is, let me show you. So uh, I will decrease. So we know that I is equal to m r square. So if the person has withdrawn his arms, that means r is going to be decreased, smaller, which in turn will decrease the I, moment of inertia. So moment of inertia will have to be decreased, and omega is bigger in this case. You can explain and think about why omega will become bigger. What is the need for omega to be bigger if I is decreasing? Okay, so if you can see clearly here that angular momentum remains the same. So the value of L has to remain the same. In order to do that, in this case, omega has to increase. That means person will now be observed. You can observe the person to be rotating at a much higher angular speed. Its speed will increase. Why? Because so that the L remains constant with this L. So I is decreased in this case, so that I is decreased, so omega has to increase, so that L remains constant. This happens because of the nature's law of conservation of angular momentum. Let me take another example here. So let's in a tornado, see what happens in a tornado, that the more further you are away from the tornado, the more safer you are. That's very obvious thing to say. And what happens in the case of tornado or cyclones, that when the air rushes inside, see, when the air is rushing inside towards the tornado, the moment of inertia decreases. Moment of inertia decreases because the value of r from the axis of rotation is decreasing. So r is decreasing, so I in overall will be decreasing. So if the moment of inertia is decreasing, to conserve the angular momentum, the angular speed of the air increases. I have written decreases here. It will be actually increases. That means near the center of our tornado, around the center of axis, the air's velocity, angular speed is very, very high. It's very, very high. Okay, because the r has decreased, so omega has to increase to keep the L constant. There's one more thing I would like to add. I'm not 100% sure, but at the eye of the tornado, we have to confirm it, but let me tell you, at the eye of the tornado, they say that it's very calm. Calm at the eye of the tornado, at the axis of rotation. Can you reason out why at the eye of the storm, at the eye of the tornado in this case, the it is very calm. Like there is no much wind, only around it. That there is a lot of high omega, high angular speed. Why at the center it is very calm? Actually, what happens there is that the angular momentum of the air at the center has to be zero, will become zero. This is my conclusion, that it has to be zero because the r itself has become zero. So I has become zero at the exact center. That's why the our velocity of air, that is the angular momentum of the air, will be zero at the exact center of the tornado. Okay. Um, yeah. So these are the two examples for this, and I would like you to try this out. This question here, I will read it out, and here you can apply. This is this example here. You can use this illustration to imagine what they're asking in this question. So let me read it for you. So a man is standing at the center of rotating table, just like this here, and arms stretched outward. This case. And the table is rotating freely with the angular speed of 24 revolutions per minute. See, they have given the revolutions per minute. They have that means they have given the frequency with which the rotation is going on. If you have the frequency, you can figure out the time. This time is the reciprocal of frequency. So I have given a hint there. You can use that. And they have given angular velocity with 24 revolutions per minute. You have to find the answer in per minute only. So now the man withdraws his hands. See what he has done now. So what he has done is he has done this pose here. So he has withdrawn his hands towards his chest and thereby reduces moment of inertia by 3 by 5 times. See, I for both is their relation is given. There was I before and I now. So it has now become 3/5 of the original moment of inertia. We have to calculate the angular speed of the man when he withdraws his hands. I would like you to try this out using the conservation of angular momentum. And the second thing you have to use is to use the omega is equal to 2 pi mu, or in other words, this relation you can use, and the conservation of angular momentum. So in order to figure this out, please give it a try. And one last question. Yeah, so this is the question. It is the application question regarding the same one that we did earlier. So we did this question here, right? The earth was suddenly contracted to half of its size. Here is a similar kind of question. So a sun rotates around itself in 27 days. And what will be the period of revolution if sun were to expand twice its present size? So sun itself is expanding now. The mass has, the mass, no, the radius now has become twice. You can consider sun as the uniform sphere, and it's not a hollow sphere, so it's a solid sphere. So 2 by 5 mr square will be its moment of inertia. I would like you to try this question just like the question that we did earlier. Okay, this is for this session now. We have 2 practice questions. Please give them a try and leave your answers in the comment section. And we did some examples here. We understood the conservation of angular momentum using the real life examples. and we have derived the angular momentum of a rigid body in case of rotation about an axis, about a fixed axis, which we concluded to be I omega. L is equal to I omega. And how we can use this to figure out um, uh, different questions and figure out many natural phenomena that we observe in the universe. Okay.